This video is going to be on trigonometric integrals. So these are integrals that involve trig functions. And let's just do a little bit of review on some trig identities that I expect you to know. So some stuff that I expect that you know. I expect that you would know that the tangent is sine over cosine, and that cotangent of x is cosine of x over sine of x. And I would expect you to know that secant of x is 1 over cosine, and that cosecant of x is 1 over sine. Okay, so those are some basic formulas that I expect you to know. I also expect that you would know that sine squared of, let's say, x plus cosine squared of x is equal to 1. Now, from this formula, there's two more. I would expect you to know that, or formulate that tangent squared plus 1 is equal to secant squared. Now this isn't one that I have memorized. What I do in order to figure this one out is I start with the sine squared plus cosine squared equals 1. I have that one memorized. And say I want to get to secant, which means that I've got to divide by cosine. So what I'm going to do is divide each one of these terms by cosine squared. So I'm dividing that by cosine squared. I'm dividing that by cosine squared, and I'm going to divide that by cosine squared. So you can see that this first term is sine over cosine, and that's a tangent squared. The second one, cosine over cosine cancels and we get 1. And on the right-hand side, we've got 1 over cosine. 1 over cosine is secant, and we get secant squared. Now, if you took that formula and divided by sine instead, so if we took sine squared and divided by sine squared, that would be 1. If we divide cosine by sine, we get cotangent. So plus cotangent squared. And that is going to equal 1 over sine, which is cosecant. Cosecant squared. Okay, so far we've got, so those top formulas there. Got all these formulas with the squareds in them. And then I would also expect that you would know some derivatives and therefore some integrals. So like I expect you to know that the derivative of sine is cosine. I expect you to know that the derivative of cosine of x is negative sine of x. I would expect you to know that the derivative of tangent of x, I would expect that you would know that this is secant squared. I expect, there's 3 more here, the derivative of cosecant of x is negative cosecant, cosecant of x times cotangent. Let's see, what other functions do we have in there? Secant. So the derivative of secant is secant tangent. And there's one more, so I'm going to squeeze it down here on the bottom, one more derivative of a trig function, the derivative of cotangent of x. And the derivative of cotangent is negative cosecant squared. I do expect you to have all of these memorized. So these are the things that I expect you to know. Now, because you know that the derivative of tangent is secant squared, you then can figure out that the integral of secant squared is going to be tangent. So likewise, I would expect you to know what the integral of negative cosecant cotangent was, that would be cosecant, and I'd expect you to know that the integral of secant tangent is secant. Okay, so now that we have that, I'm going to do a few and break this down into some integrals with only sine and cosine in them for right now, so we can get the idea of kind of how this works, and then I'll do an example with some tangents and secants in there. All of these integrals are going to they're easily recognizable. They've got sines, cosines, tangents, secants, and no other functions. So no other functions of x in there, natural logs, e's, nothing else. Just sines, cosines, tangents, secants, etc. And the idea of these is to use those trig formulas to then be able to do a u substitution. All right, so I separate these kind of into three different categories. So the first one is if one exponent is odd. And actually, if one exponent is not just odd, but is 1 specifically. And what I'm talking about is the exponent of sine or cosine. So if one of those has an exponent of 1, in order to do the integral, you are simply going to do a u substitution. And we had one of these on the review, so this shouldn't be too much of a stretch for you, but let's do an example anyways. Let's look at the integral of the sine of x cosine to the 10th of x dx. Okay, so notice on this one that the sine has an exponent of 1, right there. There is an exponent of 1. So to do this integral, we just need to do a u substitution. If we choose u as cosine, then du would be negative sine of x. So sine of x and sine of x dx, sine of x dx, sine of x dx. So we can rewrite this by plugging in that sine of x dx is negative du. And then we've got cosine, which is u, and that was raised to the 10th. Right, so we just simply did a u substitution. The integral of u to the 10th is u to the 11 over 11. We still have that negative out in front, and now we just plug back in u. We would get negative cosine to the 11th of x all over 11, and then we'd add c. Okay, so it's pretty easy. If one of them has an exponent of 1, choose the one that doesn't as your u, and you should be able to do just a u substitution. Now, if one of them doesn't have an exponent, and let's say both have, both exponents are, one or both are odd. Sorry. One or both exponents odd. So if this happens, then you first have to use a trig formula. And all of these examples I'm doing right now are just with sine and cosine. I'll say that again. So because we're doing with just ones with cosine and sine, we would use that sine squared plus cosine squared is equal to 1, and then a u substitution. All right, and the trick is kind of in where to use, what to substitute in for. Do we substitute in for sine squared, or do we substitute in for cosine squared? So let's do an example of how this might work. So let's look at the integral of sine to the 5th times cosine cubed. All right, so for this one, what I want is at the very end, I want one of these to have an exponent of 1. If I'm going to do the u sub, I need to have it look like number 1. I need to have it have an exponent of 1. I always find the smaller one to be a little bit of an easier calculation, but it doesn't honestly matter. So what I'm going to do is rewrite this. Sine is still in there. But I'm going to rewrite this as cosine squared times cosine. And that is because I want that exponent of 1 in there so that I can do the u substitution and have that be my du. All right, so now once I have that done, now see that I have this cosine squared in there. And so I can solve for cosine squared here and make that substitution. Oops, sorry, I still want that to be black again. All right, so sine to the 5th. And then for cosine squared, I'm going to substitute in 1 minus sine squared. I still have that cosine of x. And that 1 minus sine squared came from solving for cosine squared and plugging it in right there. Cosine squared is 1 minus sine squared. All right, so now I have an exponent of 1, and I can do a u substitution. So I'm going to choose my u to be the one that doesn't have an exponent of 1. So in this case, u is going to equal sine. So derivative of sine is just cosine. And now I can substitute in. So I'm going to have the integral of u to the 5th, because that was sine to the 5th, times 1 minus u squared, so that's sine 1 minus sine squared, and cosine of x dx. Cosine of x dx is just equal to du. Okay, so now a new integral. Got all u's in it, and it looks like I need to multiply through before I do this integral. So I'm going to multiply through u to the 5th, and now I can integrate that. So u to the 6th over 6th minus u to the 8th over 8, and just adding 1 to each of those exponents, dividing by that number. Now I started with x's, I need to end with x's, so I've got to resubstitute back in, and u was sine. So sine to the 6th over 6th minus sine to the 8th over 8, and those are all signs of x's, and then we'll add z. Okay, so we've looked at what happens when we only have an exponent of 1 and we just do a u substitution. If they're both odd, then we somehow need to reorganize our sines and our cosines to make one of them be an even one, so we can use the sine squared plus cosine squared equals 1 as a substitution, and then get an exponent of 1. Okay, all right, so now the example that we haven't dealt with yet, or the case we haven't dealt with yet, is if both exponents are even. Both exponents are even. If both exponents are even, what you're going to use is, this is another trig formula, and notice I didn't write this on the ones you need to know. I will give this one to you. It's called a half angle formula. Sine squared is 1/2 minus cosine of 2 times x all over 2, and sine, oh, I'm sorry, that should be a cosine. I just did sine. And cosine squared is going to be 1/2 plus cosine of 2x over 2. And the only thing to make note in these formulas, if this were sine squared of, I don't know, say 3x right there. So if it were a sine squared of 3x instead of just x, then you would have cosine of 6x right there. It's 2 times whatever is inside that sine part. Okay, so those are the substitutions that you'll make if both exponents are even. So let's do an example. Let's look at the integral of sine squared times cosine squared. So we can't make one of these have an exponent of 1 and do u substitution, because if we have an exponent of 1, one of them is left over. So that's why we have to apply these kind of new formulas. So I'm going to plug in the formulas. Sine squared is 1/2 minus cosine of 2x all over 2. So that's sine squared. Cosine squared is 1/2 plus cosine of 2x over 2. Now I don't know how to do this integral yet. I actually have to multiply everything through. So 1/2 times 1/2 is 1/4. Then I've got 1/2 times a positive cosine of 2x over 2, and 1/2 times a negative cosine of 2x over 2. Those are going to cancel because one of them's positive, one of them's negative. Then I've got negative cosine of 2x over 2 times positive cosine of 2x over 2. So that gives me a negative cosine squared of 2x all over 4. And I can integrate 1/4. That's not so bad. But integrating this guy, check it out, I've got another even exponent right there. So I'm going to have to apply this formula again. All right, here we go, again. The 1/4 stays as 1/4. I'm going to put that 1/4 that's in the denominator outside all of this as negative 1/4. And then cosine squared of 2x, so the formula for cosine over here is what I'm using, 1/2 plus the cosine of 2 times whatever's inside here. So now that becomes a 4x all over 2. Okay, I'm going to simplify just a little bit, just because I have a 1/4 minus 1/8. So here I've got 1/4 minus 1/8. So that would be an 8, that would be a 2. 2 minus 1, I'm going to get a 1/8. And a minus cosine 4x all over 4 times 2, which is 8. Okay, so now notice I haven't even integrated yet. All of that was just substitutions and algebra in order to get to something that is now integrable. I'm going to make that a parentheses to clarify. All right, so if I integrate 1/8, I get 1/8 x. The integral of cosine is sine. But because of that 4 in there, I've got to divide by the derivative of the inside part, and that derivative is 4. So I'm going to divide by 4, and I've got an 8 right there right now. So that makes 8 times 4, that would be 32. And there's my integral. Okay, so now all of these were examples with just cosine and sine, but any of these can be extended to integrals with other trig functions in there. So let's just do another example. Let's take the integral of tangent to the fifth times secant to the fourth. Now, I am eventually trying to get to a u sub. So that's kind of my first thought. When I search through this integral, when I look through this integral, I'm thinking, what can I u sub in there? What would I take the derivative of in order to get something to substitute? So what pops into my head is that I know a derivative of something is secant squared. Right? So I know, let's use a different color. So I know that the derivative of tangent is secant squared, right? Because you guys have that memorized? Okay, so I know that that happens. So let me just kind of work with that in here and see if I separate this out into, I want a secant squared, so that would leave me another secant squared with that secant to the fourth. Right? And I want to, so to speak, I want to save this guy for the u sub. Okay, so now the question is that secant squared, can I get that in terms of tangent? Okay, so now we have to go back to those other formulas, and if you look back to the beginning, we said that tangent squared plus 1 is equal to secant squared. All right, so I can make that substitution in there. I'm going to do that. So tangent to the fifth, that's fine, that stays as is. Secant squared, we know that that is tangent squared plus 1. And then I'm going to leave that secant squared. All right, so with this, I can now do a u substitution, because if I choose u as tangent, then du is secant squared. So secant squared and secant squared dx becomes du, and then I've got the integral of u to the fifth times u squared plus 1 du. Multiply through u to the fifth, u to the seventh plus u to the fifth. And then integrate, so that would be u to the 8th over 8 plus u to the 6 over 6. And I started with x's. I've got to go back to x's. And so that means I need to substitute back in u, which was tangent. So I get tangent of x to the 8th divided by 8. Plus tangent of x to the 6th divided by 6, and then we'll add c. Now, what's really interesting about these integrals is that this is not the only way to do this integral. In fact, it is very possible to separate that integral into, let's see, what would I do there? I would use one of the tangents, so I'd be left with 4 of them, and I'd use one of the secants, I'd be left with 3 of them, and so I used one of the tangents, one of the secants, and choose u as secant, because then du is secant tangent. This is just a different u substitution. What's a little confusing is that you will end up with a different answer if you do it this way. Your answer will have all secants in it instead of tangents. Now, using trig formulas, we could equate the two. We'd essentially get the same answer, but at a first glance, it doesn't look the same. And the reason I'm mentioning it is because if you go into Wolfram Alpha and plug in this integral, I don't know whether it would give you what I got here. Integrals are not unique, and you can come up with different solutions, different antiderivatives, depending on the u substitutions that you do, or different substitutions that you do. All right, so just be careful with that. Okay, so I think that's about it. In summary, we took a look at functions with only sine and cosine first, so we could get an idea of how the u substitutions work. Sometimes we have to do some kind of fidgeting around with trig formulas first, and then do a u substitution. And then you can use that for any sort of integrals with just trigonometric functions in them.